Tachyons are particles that would travel faster than light. According to Einstein's relativity, faster than light would mean backwards in time. Many physicists therefore think tachyons cannot exist, given the absurdity of their presumed ability to send messages to the past. Nevertheless, I and a handful of other physicists think otherwise. Our intrepid band of tachyon hunters has published evidence that a certain well-known subatomic particle, the neutrino, is in fact a tachyon. Gaze into the depths of time and you'll learn all about tachyons, the evidence for their existence, and why, crazy as it sounds, I think I may have received a message from the future. This is the wild and crazy guy whose relativity theories challenged our common sense ideas about time. Most people's view of time includes the belief in a sharp distinction between the past, present and future. Einstein, however, referred to that distinction as only a stubbornly persistent illusion. In his relativity theory he showed that sometimes events you regard as being in the past can for me be in the present or future, and vice versa, so the time order of events can in some cases depend on who is observing them. A key point of relativity is that no material object can travel faster than light, or in Einstein's words, faster than light speeds have no possibility of existence. Einstein was referring here to light speed in vacuum, which is nearly 300 million meters per second, and is represented by the letter c. Let's first see why Einstein made his strange claim about c being a universal speed limit. We'll then see why, despite this speed limit, particles moving faster than light might still exist. As a teenager, Einstein imagined himself chasing a light beam, which he knew to be electric and magnetic waves at right angles. If he were able to travel at the same speed as the light wave, it clearly would appear to be at rest. This is just like if your car moves at the same speed as another car, it appears at rest. Einstein also realized that such a thing as a stationary light wave was absurd. From his imaginary light-chasing example, he concluded that it should not be possible to catch up to a light wave. This inability to reach light speed was why Einstein concluded the speed of light, c, was a universal speed limit. The idea of a universal speed limit does sound crazy. For example, let's say you were aboard a spaceship that had an engine thrust which accelerated the ship at 1 g. This means the ship would increase its speed by about 10 meters per second each second. At that rate of increase, you'd think it would take 30 million seconds or around 1 year to reach a light speed of 300 million meters per second. In fact, that is just the answer Isaac Newton would give, but it is incorrect. It is wrong because Einstein showed that the mass of the ship would grow the higher its speed. In fact, the mass and energy both approach infinity when the ship's speed approached c, making light speed unattainable for the ship. We see here a graph showing how the energy of an object increases with speed according to Einstein. In 1962, George Sudarshan and two colleagues used the same mathematical function for values of speed v greater than c, and the graph of their result is almost a mirror image of the v less than c case. But, notice how for speeds above light the energy of an object increases as its speed decreases, and like the original graph the energy also becomes infinite at speed c. As a result, the speed of light now becomes a two-way speed barrier. Normal matter can never reach light speed, and tachyons with v greater than c could never have their speed drop below c. One strange property of tachyons we have glossed over follows from the mathematical function for their energy E. When v exceeds c, the expression under the square root will be a negative number, meaning that the denominator is imaginary. The m in the numerator also must be imaginary in order that the energy E of the particle is real. Imaginary mass, of course, means that the mass squared is negative. So why do tachyons not conflict with Einstein's ban on faster-than-light speeds? When Einstein said that such speeds were impossible, he was speaking only of particles that were slowly accelerated from speeds below that of light. Thus, Einstein himself opened the door for a tachyon loophole, because he admitted having nothing to say about particles that always moved at speeds greater than light from the very moment of their creation. Tachyons, if they exist, could be created the same way normal particles are created from high-energy collisions in which energy is converted into mass, according to Einstein's famous E equals mc squared. But, this fact does not mean it takes an imaginary amount of energy to create a tachyon. So how do tachyons fit into our current understanding of the fundamental particles making up our universe? It was once believed that there were only three subatomic particles, the electron, neutron and proton, with the latter two residing in the atomic nucleus, which is 10,000 times smaller than the atom itself. We now know that while the electron is a fundamental particle, The neutron and proton are not, and they each consist of three so-called quarks bound together. Here is an animation of a proton with the three quarks comprising it. The size of the quarks in the animation are way too large, since they should be 10,000 times smaller than the proton itself. Quarks come in 6 flavors, and they are among the 17 fundamental particles making up the standard model of particle physics. Here are the 17 particles in the standard model with the 6 weirdly named quarks shown in the top half of the outer ring. Only 3 of these 17 particles might be tachyons, namely the 3 types of neutrinos. These appear in the right bottom quadrant of the outer ring and are designated by the Greek letter nu. Neutrinos are the most abundant particles in the universe, and yet they are the least understood. The 17 particles shown each have twins known as antiparticles having the same mass but opposite sign electric charge. Thus, for example, the electron's antiparticle is the positively charged positron, E+, which has the same mass. The antiparticles of the 3 neutrinos are known as antineutrinos, and they are represented by a nu with a bar on top. If some neutrinos are tachyons, then of course, their corresponding equal mass antineutrinos would also be tachyons. So why are the neutrinos the only known particles that might be tachyons? That's because of how difficult it is to observe these ghostliest of all the particles. They can even pass through a lengthier thickness of lead without being absorbed. In addition, neutrinos have a mass squared that is so close to zero, we do not yet know if it is positive or negative. Likewise, the measured neutrino speed is so close to light that we do not yet know if they move a bit faster or slower than light. Before continuing our inquiry of whether neutrinos are tachyons, it is useful to recall why these ghostly particles were first proposed by Wolfgang Pauli. In 1932, when Pauli proposed the neutrino, all subatomic particles were believed to be positively or negatively electrically charged. In proposing the existence of a new neutral particle, Pauli apologized for being very bad, since he thought he had proposed a particle that could not be observed. Pauli, however, had underestimated the ingenuity of experimenters, who in fact did observe neutrinos from a nuclear reactor more than 2 decades later. What is it that led Pauli to commit his very bad deed of proposing the neutrino? Atomic nuclei are now known to consist of some number of protons and neutrons. Some nuclei are radioactive or unstable when a neutron turns into a proton and an electron. In this process known as beta decay, the radioactive nucleus emits the electron. For this emission to occur, the initial nucleus must be heavier than the final one by an amount m, so that the emitted electron acquires an energy E based on Einstein's E equals mc squared. As a result, you'd expect the emitted electrons to always be emitted with the same energy E from one nucleus to another, but that is not what is found. Instead, electrons are emitted with a range or spectrum of energies. On very rare occasions they have the energy expected based on E equals mc squared, but almost always their energy is less than this maximum value. The peak of the spectrum represents the most common electron energy, and the difference between the maximum value and the observed value is what is labeled as the missing energy. Where did the missing energy go? Pauli guessed that some unobserved light-neutral particle must be emitted in beta decay along with the electron to account for this missing energy. He originally called the particle the neutron, a name that was later changed to neutrino, after the name neutron was given to another particle. You might wonder how the ghostly neutrino could ever be observed. One modern neutrino detector, known as Super Kamiokande, is filled with 50,000 tons of ultra-pure water. Its location underneath a mountain in Japan serves to shield the detector against cosmic rays that could mimic neutrino interactions. Its huge size can be judged based on the small boat on the right. The detector needs to be very large because neutrinos and antineutrinos interact so rarely with matter. Occasionally, an incoming antineutrino will hit a proton in the water, creating a neutron and a positron that goes roughly in the neutrino's original direction. If the positron has enough energy, it will create so-called Cherenkov radiation, a cone of visible light. This light would then activate a circular ring of photosensors lining the walls. For the detections to be frequent, we also would need a very intense source of neutrinos. One intense source of neutrinos is the collisions of the counter-circulating proton beams in the LHC accelerator. The LHC, or the Large Hadron Collider, is located at CERN Nuclear Lab, on the border between France and Switzerland. The proton beams of the LHC are steered around the 17-mile circumference of the machine by magnets, and the beams collide a billion times per second. Many new particles are created from the collision energy, perhaps as many as 20,000 from a single collision. If those particles pass through a large thickness of the Earth, virtually everything but neutrinos will be filtered out. The most direct way to see if neutrinos are tachyons is to send bunches of them created in a particle accelerator over some precisely known distance. You could then see if the bunches arrive at a distant location sooner than light. This measurement was done in 2011 in an experiment at the LHC known as OPERA. The initial OPERA result claimed neutrinos were a bit faster than light, but unfortunately, the result was a mistake due to a loose cable and a clock that ticked too fast. When the measurement was redone, the neutrino speed was consistent with light, possibly a bit more or less. Consistency with light speed therefore did not show neutrinos were not tachyons, only that the issue remained unresolved. There are many other ways we could try to determine if neutrinos are tachyons, and here are 4 of them. Since tachyons have an imaginary mass or a negative mass squared, we could measure the neutrino mass squared as accurately as possible. Secondly, we could check if low-energy neutrinos travel faster than high-energy ones, which is only true for tachyons. Thirdly, we could see if neutrinos emit Cherenkov radiation in vacuum, which is also only possible for tachyons. The strangest of the 4 listed ways is to look for evidence of neutrinos going backwards in time. What on earth does that even mean? If a neutrino was emitted from some reaction, a backwards in time neutrino would mean it was instead absorbed in the reaction. This is much like the tachyon bullets entering the gun instead of leaving it. Believe it or not, there really is a process very close to a gun firing tachyon bullets. A key aspect of relativity is that the 3 dimensions of space and the 1 of time form a 4-dimensional spacetime. Here we see a spacetime diagram where only one of the 3 dimensions of space is shown, and the units of space and time are light years and years. This choice of units means that an object traveling at the speed of light is represented by a 45-degree sloping line, since it would travel 1 light year in 1 year. One of the surprising aspects of relativity is that the order of events in time can depend on your motion. For example, depending on your speed, the 3 events, A, B and C may appear simultaneous, or alternatively they may appear in the order, C, B, A, or the reverse, A, B, and then C. These changes occur because when you move at different speeds, the lines of constant advancing time are no longer horizontal but inclined. One place to look for evidence of backward time traveling neutrinos is in the cosmic rays. These consist of particles that bombard the Earth from space. Cosmic rays are found to be mostly protons with a small mixture of alpha particles and heavier atomic nuclei. We are not yet sure where they come from, but we do know that they have energies in some cases millions of times greater than any accelerator can achieve. If some neutrinos are tachyons, they might exhibit a backward-in-time behavior only at very high energies, otherwise this behavior probably would have been seen already in accelerator experiments. Therefore, it makes good sense to look for backward-in-time neutrinos in the very high-energy cosmic rays. Let's see how a backward-in-time neutrino could be identified. Here we see 2 conceivable beta decays, namely that of a free neutron and a free proton. The relative sizes of each particle mass is shown by the sizes of the circles, the neutrino being the small black circle next to the E plus or minus. Only one of these 2 beta decays is allowed by conservation of energy. Do you know which? Remember that by E equals mc squared you can only conserve energy if the final mass is a bit smaller than the initial mass. Congratulations if you concluded that the neutron decay is the allowed one. On the other hand, if the neutrino is a tachyon and can go backward in time, the proton decay will also be allowed. In order to explain why a normally forbidden proton beta decay becomes allowed, we need to rely on a pair of spacetime diagrams. Here is a spacetime diagram depicting beta decay of a proton for someone watching the proton zip past at extremely high speed. Let's see how the process looks as time advances. At a certain time the proton disappears, and the neutron, positron and neutrino suddenly appear, and then they all move away from each other. But the process looks quite different from the point of view of someone moving with a proton for which it appears at rest. Here is how the process appears to someone moving with a proton who sees it at rest. For this person, the advancing constant timeline is no longer horizontal but it is inclined. Notice how the neutrino is now seen to be an incoming not an outgoing particle, just like that earlier gun shooting tachyon bullets. The process appears to be an incoming antineutrino from space colliding with a proton and creating a neutron plus a positron. This reversal of the neutrino direction and having it be seen as an incoming antineutrino, is what we mean by the particle going back in time, but recall that such time reversals only can occur if the neutrino is a tachyon, and only if the proton is moving fast enough. Now let's see how this backward in time behavior can be observed using actual data, namely the measured shape of the cosmic ray spectrum. A and B are the so-called knees, which are sudden downturns in the spectrum. The first knee at A can be interpreted as a sudden loss of protons due to increasing numbers of them undergoing beta decay above a certain energy. The second knee at B can be interpreted in the same manner, but in this case for alpha particle decay. The energies of the two knees at A and B are exactly what one would expect for a tachyon neutrino having a specific imaginary mass. Finally, the sudden upturn in the spectrum at C can be understood in terms of more and more undecayed protons reaching Earth from increasingly distant sources, as a result of so-called time dilation. Aside from cosmic rays, a very good place to look for evidence that some neutrinos are tachyons is the supernova. These massive explosions occur at the end of a star's life for stars much more massive than the Sun. Supernovas are so energetic that for a few seconds the exploding star outshines the hundreds of billions of stars in their entire galaxy. Supernovas are also prodigious sources of neutrinos. Since most of the neutrinos are emitted during only a few seconds, measurements of their arrival times and energies give us good information on the neutrino speed and mass. Unfortunately, however, only one supernova has occurred in our galaxy during the era of neutrino detectors. This was SN 1987A, observed on February 24, 1987, when the star known as Sanduleak exploded. Around the time that Sanduleak was observed to suddenly brighten, 3 neutrino detectors around the world recorded sudden bursts of neutrinos all within seconds of each other. But that is not the whole story. A fourth detector located under Mont Blanc in the Alps also recorded a burst of neutrinos on the same day as the others, but this burst was about 5 hours earlier than the other 3. For that reason, the Mont Blanc burst is usually ignored. An alternate explanation is that the 5-hour early neutrino burst had a speed exceeding light by about 0.01%, and that one of the 3 flavors of neutrinos are tachyons. Another supernova in our galaxy could provide the definitive evidence that some neutrinos are indeed tachyons. But these events occur only about twice per century. You might think that since the last supernova occurred 36 years ago in 1987, we are now overdue for another, but probability doesn't work that way. A long string of years with no supernova makes it no more likely that the next year will reveal one. Of course, there are many supernovas occurring every year in other galaxies, but they are too far away to observe many neutrinos from them, so the best near-term hope in resolving the matter of some neutrinos being tachyons anytime soon would be a lab experiment. A good test of whether some neutrinos are tachyons would be the KATRIN experiment being done at the Karlsruhe Institute of Technology in Germany. The amazing photo shows the experiment's main spectrometer, being hauled through a nearby town en route to the lab in 2010. This perilous portion of the trip was necessary given the location of the fabrication facility for the device relative to the lab. German roads could not accommodate such a large piece of equipment, which required a route mainly over water and an elaborate 8,600 kilometers detour. Fortunately, neither Hans or anyone else lost their head during this final part of the trip. KATRIN seeks to measure the mass of the neutrino, or actually the antineutrino for which only upper limits yet exist. Let's now see how the mass is found. KATRIN measures the electron neutrino mass based on the detailed shape of the beta decay spectrum very close to the endpoint. Results to date show the neutrino mass is less than a millionth that of the electron, the lightest other particle besides the neutrino. Unfortunately, however, m² is so close to zero that within uncertainties we do not yet know if is positive or negative. The results are also consistent with the so-called 3+3 model involving one of 3 neutrinos being a tachyon. Additional KATRIN data may resolve the ambiguity and find either a positive or negative value for m². One can only hope if KATRIN does find a negative value, namely a tachyon, the result will not be dismissed as unphysical, as has happened with some earlier experiments. While astrophysical observations suggest that some neutrinos are tachyons, lab experiments on neutrinos still yield ambiguous results. Why the ambiguity? As already noted, the neutrino mass is so close to zero that we do not yet know the sign of m². However, given the value for the imaginary mass implied from astrophysical data, we should be very close to observing it experimentally in the lab. In some respects, experiments to measure whether neutrinos are tachyons are like looking for ET. If we keep looking, we may just keep getting inconclusive results if m² is exceptionally small or if ET is very rare. However, it is worth continuing to look, given the importance of a positive result if one is found. The rest of this talk is the weird part, or maybe I should say the weirder part. Here we shall assume some neutrinos really are tachyons and consider how they might be used to send messages back in time. I'll also discuss the crazy possibility that I may have been the recipient of such a message from the future. But first, let's consider why, if messages from the future are possible, receiving them is not a common experience. We know this is true based on the very few casinos going broke, and the very few multiple lottery winners. If sending messages to the past were ever possible, this would raise various paradoxes. For example, suppose a future budding scientist reads a book on relativity. In doing so, she became aware that Einstein unsuccessfully spent 2 years looking for an academic job after his graduation. Feeling sorry for the young Einstein, she sends him information about relativity before he devised the theory. The dejected Einstein becomes very happy, and he publishes relativity under his own name. Einstein becomes world famous for a discovery he did not make. The girl in the future was of course not the originator of the theory either, since she learned of it from a book. The question then arises, where did the theory come from? Paradoxes like this one do not necessarily mean something is impossible, only that they just seem that way. There are many reasons why there are so few messages received from the future, the simplest being that this ability, also known as precognition, does not exist. It is also possible that only certain gifted people can receive such messages, or perhaps they happen only in extreme situations, such as in premonitions. Alternatively, the signal is usually hidden by the noise. Regrettably, any initially positive results of such possibilities have later been found to be the result of fraud, bad experimental controls, or flawed statistics. There are simply no replicable precognition experiments. Assuming messages from the future really are possible, one dismal explanation for their non-existence is that we have little future left. A much more optimistic explanation is we just do not yet have the technology to receive them. Here is how you might conceivably use tachyons to send a message to your past self using a ring of orbiting satellites. The tachyon message is first relayed from the tower to the nearest satellite, which instantly relays it to the next one, and so forth, continuing around the ring for many loops. To send the message further back in time, you'd increase the number of loops the tachyons make. The choice of satellite and tachyon speeds is also important. Just to take an example, if the tachyon speed was 27 times the speed of light, messages would not go back in time at all unless the satellite speed was at least 1/27th the speed of light. The feasibility of this scheme is completely unknown, and it depends most importantly on whether tachyons exist. But even if the scheme is feasible, it could not send messages back to times before the system were built. A second method for sending messages back in time has no need for tachyons, and is not limited regarding how far back messages can be sent. Instead, it relies on wormholes, which are consistent with Einstein's relativity, but as yet never observed. Wormholes are similar to black holes, which represent extreme distortions of space and time in their vicinity. But unlike black holes from which there is no escape, if you enter a wormhole you can come out the other end of a tunnel that may connect two remote regions of space or time. Conceivably, some advanced civilization could use wormholes to communicate across time using a stream of ordinary particles to transmit information. It is also possible that a spaceship could traverse the wormhole tunnel and visit the past, but that might be much more hazardous than just sending signals.
I hope this message finds you well. As someone who is living in the year 2050, I want to share some insights with you about what the future holds. First and foremost, I want you to know that despite the challenges we face, humanity is still thriving. Advances in medicine have allowed us to extend lifespans and improve the quality of life for many. In fact, some people are now living well beyond 100 years old. Although you may feel like your time is limited, I encourage you to cherish every moment and make the most of your remaining years. Spend time with loved ones, travel to places you've always wanted to see, and pursue your passions. Finally, I want to assure you that your legacy will live on. The wisdom and experiences you've gained throughout your life will continue to impact future generations long after you're gone. Take care and enjoy the time you have left.
That is the message I recently received when, just for fun, I asked ChatGPT to write a 150-word message from the future appropriate to a person with a very limited remaining time on planet Earth. While that ChatGPT response sounds pretty good, unless you put faith in fortune cookies or psychics, you would be unlikely to believe such a message originated in the future. On the other hand, in 2015 I had an experience which made me question whether I might have received a real message from the future. On November 22, 2015, I submitted a paper to the journal Physical Review Letters on a model in which one neutrino was a tachyon. Immediately after I entered the paper title, the submission system provided a much better title than the atrocious one I had entered, causing me to wonder how it could do such a thing. When I contacted the journal editor the next day, I learned that the journal in fact had no such capability for suggesting improved titles. I have no explanation for this event, and it led me to wonder if someone in the future was telling me that I was on the right track with my so-called 3+3 tachyon model and encouraging me to continue. I found the mysterious origin of the improved title far more convincing than a normal email claiming to be from the future, which I would have dismissed it as a joke or scam. Here's a brief summary of the key points of this video. In his 1905 relativity paper, Einstein banned faster-than-light speeds as being impossible. A half-century later, George Sudarshan and two colleagues found a loophole in Einstein's ban for particles called tachyons that always had faster-than-light speeds from their moment of creation. Among all the known particles, only the ghostly neutrinos might be tachyons, since their unknown mass is so close to zero. While some astrophysical observations suggest some neutrinos are tachyons, the matter may be for future experiments or a new supernova to decide for sure. If tachyons really do exist, they might allow messages from the future to be sent back in time. Assuming I am not living in a computer simulation, I may indeed have received such a message. This talk has summarized the ideas discussed in my book, entitled Hunting the Faster-than-Light Tachyon and Finding 3 Unicorns and a Herd of Elephants. The book is intended for anyone curious about our mysterious universe. It does not require you have studied any physics, but that probably couldn't hurt. The book is, in effect, a scientific detective story, and a personal memoir. But the 3 unicorns and the elephant turd don't make an appearance until about halfway through the story. If you are interested in tachyons and time travel, you also might want to check out my amusing website as well.